let's wait a little bit, maybe anyone else will pop up.
Do you still use NERSC?
Yes, I would.
Okay.
You all will do as well.
Well, I'm trying to convince Dr. Razlev to get an account there, because he's, I don't think he has one yet for NERSC.
I will, if you will not have it, I will arrange one.
Oh,
To-
awesome.
The printer stopped about at copy number 7, but if there will be no one else, then everyone will have a copy. So do not trust anyone, including the sources from literature. There could be either errors or not efficient way to communicate ideas, but in some sense, what you see is second opinion of what we're doing in class. And I have planned to share a few more ways how to verbalize this stuff. Before we go to the class materials, let's do some little organizational things. No. Too big of a star. I'll put a little star on the top. So one copy will be for me, and please leave your choices, what you want to present in 2 weeks.
Oh,
And one copy will be for you, just for your memories.
okay.
So those who will arrive later or not arrive will have less flexibility in choosing what to present. So the idea is that we will have 2 more practical sessions, labs, and then in 2 weeks from now, in like second Thursday from now, you make little, maybe 5 minutes presentation summarizing practical skills. For example, yesterday there was a little glitch in saving video recordings. But some of you may need it, and we will have, just in case, we will duplicate it by presenting these same materials, but by class attendees. Sorry. So I invite you to submit ideas and votes. So we'll practice what we want to present in 2 weeks. And in case of scheduled content, several people want to do the same subject or something like that. We'll decide how to resolve the conflicts.
What's your grading?
Huh?
What's the grading criteria for this assignment?
I'll send everyone the syllabus,
Okay.
but the major part of grading is written reports and presentations on the research project. That will be at the end. the semester. And this, the homeworks and presentations will contribute little pieces. So it's not super critical, but they're accumulating a little portions.
So but this by itself is a small portion of our grade, but it accumulates over time along with all the other things you assign us.
Yes.
Okay.
Yes. Okay, and there will be. So feel free to ask more questions right now or at the end of the meeting. And I think that some of you may miss homeworks, so I want to entertain you with a little one at the level of kindergarten.
Okay.
So please try to bring it to complete it and bring it by next class on Tuesday. But I'm sure it will take maybe 15 minutes at maximum. It's mostly demonstration that you agreed to do something rather than assessing your intellectual ability, because it is just literal follow-up of what you do in the. So there will be one copy that I will collect. This one is for your information, and there will be one for you. Okay. Whew. Answer? No? Okay, good. So I'll try to put recordings when they are available here, so that by the end of the semester you'll see recordings of all our meetings. And I can share same field sheet with field recordings from previous years if you want to watch ahead of time. I don't know if you have time and energy, maybe it's not so interesting, but who knows. For right now, for recordings, probably I need to be less humble and focus on myself. How to do it? Yeah, when you will be presenting in 2 weeks, you will enjoy this toy, and we can, if someone wishes, if there is a volunteer to play and be like focusing person, you can pass it around and focus instead of instructor on each other. So we are on Born-Oppenheimer approximation that we have just started, and there will be a couple of slides with overview of what has been done in our previous couple of meetings, right? And then we'll go further. So please take a breath for today. It will be the hardest meeting of all. The rest of the meetings will go down in the intellectual level. It will be useful, important, but today is probably the hardest intellectual part. I would say so, yes. Okay, so here the thing that thanks. I'll bring a couple from two of those and two of those homeworks and wish list for presentations. Can you please pass around so that everyone leaves? The one with star.
This one?
Yes, pass around. So this is the end equation that we are going to get by the end of coming Tuesday meeting. So it looks similar, but I don't know. I do not think that it will be good, respectful way to keep intrigue and then say, oh, what a wonder, what a nice equation. So you see it from the beginning. So our goal, you know, we'll go over it once again. We do have molecular Hamiltonian, we do have molecular Schrödinger equation, and we realize that it is too complicated. We need to split it on pieces. And first thing to go is to separate electronic and nuclear degrees of freedom. Temporarily, not for the whole life, we will respect quantum properties of nuclei, which actually is not always needed. And we already declared electronic part. You recognize some notations, and by the end of Tuesday meeting, we will get the Schrödinger equation for nuclear wave functions that we will name with this Greek letter that looks like X. You will teach me how to pronounce it several times, maybe I will pick up. Hi, Xi, whatever. Something. Okay, and these equations will summarize how we will arrive to these equations. So do not rush. I will show the same slide a couple of times more. We will slowly but surely go through things. So this is the practice of democracy that you are feeling, right? Selecting what you want to present, and at the beginning of next week I will show your choices so that you confirm that you really like them. And here is the homework that you may entertain during the weekend. Do not feel it. It's really simple. So there is an invitation for you to draw a diagram of a couple of simple molecules and write each term in the Hamiltonian. Actually, by subtracting positions of like drawing vectors from origin and subtracting stuff. So there will be two things. H2 plus, which is the simplest molecule in the world, right? So 2 nuclei, 1 electron. Everything simpler will be atoms, or whatever, ions. And you can draw a schematic, label vectors, identify which of them belong to ion-ion, electron to nuclei. And then generally you need to identify charge and mass, but if it is proton, it's trivial. And then write down the kinetic energy for nuclear degrees of freedom, for kinetic for electronic degrees of freedom. Then write all repulsion between nuclei, right? Then write all repulsions between electrons. If it will be H2 plus, there will be only 1 electron. So this term will be missing, right? And then nuclear to electron attraction. Right? So if there are 2 protons and 1 electron, there will be 2 terms like this. Then this will be super easy, like it's like entry level of kindergarten. Next one will be slightly more complicated, but also easy. Repeat same steps for lithium hydride. So it's also 2 nuclei, but few more electrons. Let's keep it as an intrigue. If you are advanced chemist, it is not a problem. If you are seeing the word chemistry for the first time, you will open periodic table of elements and count how many electrons come from lithium. Okay, so what we did previous time. Now it works. Okay, so we at the Wednesday labs we build atomistic models, and we are preparing to run correct software and correct hardware, right? And then we will get the observables that can be compared to experiment. In class, we are going through theoretical background, and here is example of your homework, but for hydrogen molecule, right? So drawing positive nuclei, drawing negative electrons, connecting them all by arrows, giving them appropriate names. You can select your own names. There is just suggestion to use uppercase for everything for heavy electron ions and lowercase for nuclei. So we admit that molecules obey quantum rules. No one was objecting, therefore it is everyone agrees on it. Right? And if you want to describe quantum properties of an object, we need to formulate Hamiltonian and plug it into Schrödinger equation. Right? So for the Hamiltonian, we need kinetic and potential energy. Kinetic for nucleus, kinetic for energies, potential for nuclear repulsion, electron repulsion, and electron nuclear attraction. This advancer works at some points of space. Probably it's like standing waves, and I need to be at the maximum of a standing wave to make it work. Or just closer to receiver. Then the terms that come into Hamiltonian, molecular Hamiltonian, which has huge number of degrees of freedom, can be rearranged. So degrees, parts of the Hamiltonian that correspond to nuclear degrees of freedom, and parts of the terms in the Hamiltonian that corresponds to electronic degrees of freedom. And there is a bad guy that belongs to both, but we take decision to merge it with electronic part. So if we do so, we can find eigenstates and eigenenergies of this electronic or quasi-electronic part of the Hamiltonian and use them as a basis to solve overall molecular Schrödinger equation. Because our goal is to, we are like ancient Romans, divide and conquer. It's too complicated to solve at once, we need to split it on pieces. And we want to separate electronic and nuclear degrees of freedom. So we are looking for a solution in the form of superposition. So this symbol means summation. Summation of all solutions for electronic part of Hamiltonian, where electronic degrees of freedom come as independent variables and nuclear degrees of freedom come as parameters. Each wave function of electronic degrees of freedom come with a certain expansion coefficient. But these expansion coefficients are not known. And our local goal is to find these expansion coefficients that are symbolized with this Greek letter that I cannot pronounce.
Chi.
Chi. That's simple. Chi. Chi sub A. So this symbol plays two roles. On one hand, it is expansion coefficients in overall solution of molecular Schrödinger equation, and on the other hand, it will be nuclear wave function. And our plan is to take this, it is the same equation, electronic wave functions and expansion coefficients. We are taking this general form and plug it into molecular Schrödinger equation. We hope that by doing so, we will be able to get rid of electronic wave functions and convert molecular Schrödinger equation into Schrödinger equation for nuclear wave functions. Okay? I feel that we are about to come to, yes, end of the what we did before. How do you get rid of wave function? Well, the simplest way is just to tear off the piece of paper and throw it away. But if we are a little bit more serious, if we carefully process some equation, it does include wave function. And we want to get rid of it without violating any rules. How to convert from a wave function to a number.
Can you use orthonormality?
Perfect. Thank you, Kevin. Anyone wants to object this nice suggestion? Everyone agrees, right? Can you briefly tell us what is orthonormality from your point of view?
Okay, just to draw like a useful analog in Cartesian coordinates, you have like three vectors, but then you know, like if you take the dot product and multiply just a regular vector in Cartesian coordinates by like x hat, y hat, or z hat, you'll get the projections in like x, y, or z. It's kind of like, I guess, the same idea here, but instead, you know, you take a wave function, you multiply by its what was I going to say? Yeah, take the wave function, multiply it by its complex conjugate, and then integrate from 0 to infinity in like one dimensions, and then you'll get 1.
I'm absolutely happy. Yes?
Is that just like literally because it's a wave function? In theory, it's just getting rid of the wave by having like the opposite wave hit it. I know. I guess I'm.
If you do conjugation, you swap the phase to opposite, and then when you multiply them, they cancel the phases.
Yep.
Become instead of complex wave functions, become real distribution. And then you integrate it over the whole space and get a number. And then if you start with good wave functions, you'll get either 0 or 1.
Mm-hmm.
Give me a little signal if this statement seems strange or you do not feel super comfortable with it.
It's been a long time.
Comfortable? No? Okay. Give me signs if you are very comfortable with this statement. Okay, give me signs if you are very uncomfortable. Give me signs if you are so-so. Okay, good. So we'll go over it. So again, who we are and where we are. We are developing equations that are behind the computational chemistry models that will generate us like observables, gaps, chemical structure, right? We already developed molecular Schrödinger equation, molecular Hamiltonian. We developed a basis of electronic states, and now we need to get an equation for nuclear wave functions. So we need to get rid of electronic wave functions, and we need to make it in a legitimate way. So legitimate way to get rid of wave functions is to practice orthogonality. Good? I should stop being humble and focus on myself once again.
I know.
Yes?
In the past, you had like a timer in the bottom left. I don't know.
What?
In the past, you had like a timer in the bottom left of the screen. I don't know if you're recording right now.
I'm trying to.
Okay. I just remember there used to be a timer.
This room has a very good reputation for reliable recordings. Another one is sometimes, but tech support will come our next meeting and make sure that recordings will go.
Right.
So all future class meetings are in here from now on?
Huh?
All future class meetings are in this room from now on?
No, this room is not available on Tuesdays and Wednesdays.
Okay,
It's available on a Thursday.
alright,
And we'll probably keep it because it is something reliable.
okay.
So all your presentations will be on Thursday so that you will be recorded for sure.
Mhm.
Okay, so it is basically summarizes what we're doing, and here is what we got. There are some empty spots that I'm going to fill. So it is what we've got after solving for electronic degrees of freedom. So this is a reminder of the molecular Schrödinger equation, if you recall it. So in Schrödinger equation, and I put it in a column, otherwise there will be no space to write. So the Schrödinger equation means that we have a Hamilton. Wait. That we do have a Hamiltonian, then the wave function, then eigenenergy, and then wave function again, right? Agree? But we already agreed that our wave function will be represented as this chi times phi with all little signs like A. And the chi depends only on nuclear degrees of freedom, and phi depends on both R lowercase and R uppercase. If I want to be meticulous and careful, I need to put curly brackets, vectors, indices. Just if we can imply that they're there and play lazy. If needed, we can put them there. So what I'm going to do is I'm going, like, if I would be a 4-year-old kid considering Born-Oppenheimer approximation, I would print this page, take a scissors, and copy this portion of formula, and then I would paste it everywhere where we have psi, here and maybe 3 times there, psi, right? So it would change nothing. It will be still Schrödinger molecular Schrödinger equation, and everything related to electronic degrees of freedom is hidden here. Do you remember what it is? Oh, let me ask better. Do I remember what it is? So if you have T sub n and V and n, probably this thing includes how many terms? 3. Which one? I'm just checking my memory. You just lean back and relax. Kinetic energy of electrons, potential energy of electron repulsion, and electron to nuclear attraction. T sub E, V sub EE, and V sub NE. Right? We just combine them. Why do I put them as just single H? There is a reason.
Because that's the most dominant part of the Hamiltonian, and that we can neglect the other parts of it.
Yes, and there is a practical reason. Because I want to be lazy as much as possible. If we act with this part of Hamiltonian onto state phi, the Hamiltonian will disappear and convert into the eigenenergy, right? So it will immediately simplify the equation. You are with me yet? Please do stop me if you do not like something.
Question, why is it HE and not HNE? Wasn't the N supposed to be in there as well?
The red one?
Yeah.
Let me write it down. So H sub E equals T sub E plus V E plus V N E. Does it resolve the question, or you still have it?
No, I think I got it. So then that's what he was saying over there, was the dominant feature was the
Yes.
H.
Yes.
Okay.
You see, we are so lucky that computers will solve actual equations for us. We are tired even to mention abbreviated terms in the Hamiltonian. Yes?
Are these two symbols the same? No, there's the phi there and
Just a second.
this, yeah.
Up top of the button.
Top one? Okay. That and that.
No, they're different symbols. Thank you.
Alright.
Thank you, Kenny.
Okay, sure.
This one is more general, this one is less general. I think I know how to pronounce them, at least 3 years of training. So this one is phi and this one is psi. So this psi or psi is true wave function of a molecule that depends on all electronic and all nuclear degrees of freedom.
Okay.
Where both electronic and nuclear degrees of freedom are independent variables. So it will be like 150 independent variables for benzene that you were drawing last time, right?
Yeah.
This one will have only this electronic degrees of freedom as independent variables, and the nuclear positions will be just parameters. So it's a little simpler function. And this one depends only on positions of nuclei.
Oh.
So I'm going to the next slide, and I hope that I was preparing well. And this portion of summation in this part will pop up here, there, and there. Yes. Any objections? No.
You saying those are equal, or like you're saying Tn is equal to what's on the right?
I don't know if this device will survive
No,
throwing.
It says Tn. It's just I'm asking Tn, and then to the right of
T
it,
sub n.
yeah, and then to the right of that is blue text. Are you saying those are equal?
No.
No. Okay. Yeah.
No.
That's what I was thinking. Yep. We're good. Just
So typically we write Schrödinger equation as H times psi equals energy, here we can call energy W, times psi, right? So there is a left and right part. This one is operator, this is energy, okay? But we are free people. Instead of writing from left to the right, we can write from the top to the bottom. Okay? So operator times psi is these three terms. Energy is here, and here is the last psi. So we are practicing liberty. And we are trying to use smart use of the space on the board. Otherwise, when I would write on the wall.
okay.
So we are writing blue fragment 4 times, right? And again, what is my goal? I don't trust my memory. I need to recall it again and again.
You're trying to get rid of this. You're trying to.
I'm trying to get rid of something.
And
there are 2 types of function, phi and chi. Which one I want to get rid of?
you don't like chi.
I like chi.
Oh, you like chi.
But I hate phi. So I want to get rid of phi, which is already known.
Okay.
We assume that we already know phi. But we need an equation that will deal only with nuclear degrees of freedom. Chi of R. And we need equation for the phi. And phi of R, nuclear and electronic, is already known. So our goal is to somehow get rid of phi everywhere, if we can. Well, first, if we will apply this electronic Hamiltonian to this superpositional wave function, we can swap orders of these coefficients and this Hamiltonian. Go right here. And then this Hamiltonian doesn't affect, since it doesn't have any differential operators that change chi, it will change only phi. And when it acts on phi, this Hamiltonian will convert into eigenenergies of electronic states. So this term will give E sub A summation of A chi A of R, something like this.
What about T sub n and V sub n, and what kind of energies will they bring?
Just a second. Please repeat the question.
What about T sub n and V sub nn? What kind of energies are they going to spit out?
Kinetic energy of nuclear motion
Mhm.
and potential energy of nuclear to nuclear repulsion. Good?
So when they act on the wave function, they'll also like spit out some energy times the wave function too?
No. Yes and no. Generally, operators spit out energy times wave function, but those indices n mean that this T sub n and V sub n will act only on chi,
Okay.
but they will not act as much on the phi. So, please be with me by hating phi.
Got it.
Get it? So now Kevin gave us great suggestion. I'll try to record his idea on a mathematical language. So if you have phi sub a r times phi sub a r del star dr integral from minus infinity to plus infinity, then let's put b here. Wait, little correction. I like a here and b there. So this construction will give us value 1 if a equals b, and will give 0 if a not equal b. Any objections? So if you were slightly exposed to like some limited amount of quantum theory, you probably have seen it, right? Orthogonality of wave functions. If you have at your disposal good wave functions, they are expected to be orthogonal. They're not mathematicians, they're not proving it, but it's like a property. If you come into the store and to shop for wave functions, you can ask like, are they orthogonal? If not, they're not costing that much. And this means that if you have one wave function, if you multiply it by another one and perform integration, we will get rid of wave function. We will implement my dream. I hate phi, and I have a way how to remove it. You see? So anytime I see phi, I will multiply it by another phi with another index and integrate. Good plan? And I always mix where is Kronecker and where Dirac. I think this one is Kronecker. And here is just a little comment, technical comment. Close your ears and eyes, do not listen because it is not important. It's technical. Since under lowercase r we assume that there are Cartesian projections of all electrons in a system, instead of writing dr once, actually it is dr first, dr second, dr third, and these phi's depend on all this electronic. But orthogonality property stays correct even in multidimensional space. We shouldn't worry. So, you see this little green symbol. So, integrate by dr from minus to plus infinity of the phi star sub b times something. So again, I am a kid, 4 years old, looking onto Born-Oppenheimer separation. I print this page, take scissors, and cut this little fragment, trying to paste it everywhere across the next page. So we had phi sub a wave function popping up how many times? 4 times. 3 times when we were practicing showing the equation in the vertical form, 3 times above equality sign, 1 times below. Each time we will multiply it by this greenish pasting component. In previous years that I was colorblind. So what I call it green, here is red. I apologize for the confuse. But still the symbol is B here. So there are boxes. So integral phi star sub B, 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 4 times, right? And here, so colors as well, whatever should be different. But there are 3 terms above equal sign and 1 term below. First term is kinetic energy of nucleus and our superpositional wave function. Potential energy nuclear to nuclear and our superpositional wave function. The electronic part and the superpositional wave function. Eigen energy and superpositional wave function. Okay? Do not worry. All other lectures after this will be easier. So you are suffering only once in the life.
Is there a reason why like the phi is not inside the derivative and antiderivative of the integral?
Well,
Like usually it would be like inside between the two. I was just curious.
Just be my director. Should I lift hand or lower the hand as a robot?
No, that was perfect where you had it.
Here?
So that symbol phi
Okay.
usually is inside of like the integral and the.
Inside what?
Inside the
So
integral.
you're saying the
Yeah.
dr is supposed to be after the phi. So
I was just asking why that would be. I'm used to seeing whatever.
Oh,
inside.
it doesn't matter.
Okay. Okay.
Because
It's
there's
like 2 times 3 and 3 times 2 is the
yeah,
same.
it's,
Okay.
Unless they're not quantum operators, you can swap the order. Good.
it's based off of
well,
multiplication.
But yeah, I've just never seen that. Okay.
phi has both little r and small r. Why is it just dr the operator?
Because uppercase R is a parameter, is not an independent
Okay, so
variable.
parameter.
We are kind of redoing this little phi for specific value of R capital, but it doesn't depend on it in true sense.
Wait, say what you said again, but could you, what was your question?
Asked why do we have just dr little r instead of
The big R?
both of them?
Why? So the excellent question, Queen. So why don't we integrate over uppercase R?
R as well, yeah.
2 reasons. First, because phi depends on R capital only as a parameter, and second, if you would perform integration over R capital, we may get rid of the chi that I love. I do not want to get rid of it. We want to keep this chi. Okay? So the integration over uppercase R is dangerous. It would undermine my dream. Okay, and now technical things. What do we do here? So for the 3rd term, we just replace electronic part of Hamiltonian acting on phi sub I will be just energy of eigenstate E sub A times phi sub A. So you're getting rid of quantum operator. For 2nd term and for last term, these integrations will be harmless, and the 1st term is most challenging.
Okay, I'm sorry.
Please, I love questions.
Okay, I kind of forgot why we hated this term.
Because we already know it. Like if we already so our starting point that we isolate kinetic energy of electrons, potential energy electron repulsion, and nuclear to electron attraction. We combine them into this electronic Hamiltonian, and we already found this phi sub A. We know them. They're stored somewhere. This problem is solved. Then we assumed superposition form of overall wave function, and now we want to find chi functions. So phi is known as chi is not known.
Okay.
And we cannot learn it before we derive equation for it. So we need equation only for chi, not for phi.
Got it.
What do we do? We are going to practice orthogonality, and we are going to get rid of this phi very quickly. Just going slowly but surely. It will be trivial for second, third, and fourth term, and it will be problematic for upper term. Just giving you heads up.
So we said we hated it because we already knew it. We wanted to get rid of it to solve for the other piece of information.
Perfect.
Okay. Okay, now I get it.
Yeah,
Great.
I cannot tell it better. Good. Whew. So, just giving you heads up, it will be shown on the slides. The last three terms will be fine, first will be problematic. And Kiveni, you know why it will be problematic. Exactly because of the parametric dependence on R capital. So this kinetic energy operator includes derivative over position of nuclei, and the electronic wave function parametrically depends on nuclear position. So although this operator is supposed to act only on nuclear wave function, occasionally it will also destruct electronic wave function as well. And this is the most challenging part. I will come back to this again and again. It's a core of this material. Okay.
So you want it, okay, so wait, go back. So you want to,
This is the most important slide. The rest are technical details.
but with the T sub n, you want to get rid of, you want to, because that's causing a problem because of the big R, because of the position.
Because T sub n includes derivative over big R,
Yes.
it will typically all these operators in the equation for chi should affect only chi function.
Okay.
Like here, this constant will not affect phi. Here, this eigenenergy will not affect phi. It will be fine. Here, it is just this nuclear energy depends on R, and it's just multiplication. But here, there is this T sub n. Let me bring it up. Please raise hands if you are perfectly happy, if you are ready to write down kinetic energy operator in differential form.
Kinetic energy operator in
Either derivative of something in differential form.
one or three dimensions.
Well, at least in one.
Okay.
Okay. 1, 2, 3, including me. Okay, who has an idea how to do it with Google or with previous lecture notes? 1, 2, 3, 4. Who has no idea what I'm talking about?
Needs review.
Okay, okay, yeah. So this is the this class is very simple in practical sense, but in terms of quantum theory, it's a little advanced. This part will be not part of any exam. It's just for our awareness. If we would be in the basic quantum theory class, there is only one equation that one needs to memorize. The rest of equations can be derived out of. And this the only equation that one cannot survive in the basic class is this one. Kinetic momentum, quantum momentum, is derivative over position times Planck constant and imaginary unit. Right? You didn't catch me lying because I was not lying. And if you need kinetic energy, you do momentum squared over 2 masses. So instead of first derivative, it will be second derivative. So anytime we are speaking about kinetic energy in quantum language, we assume second derivative over position. Okay? And here it is kinetic energy of nuclei, therefore it will be derivative over position of nuclei rather than electron. Any questions? This is most important slide. Rest are more technical.
Okay, I'm sorry. I'm going to have to ask
Please.
this again because this has been a long time for me. So, if you could say what you said on the right-hand side with the position starting there, that most important equation, right? And how it relates.
For this class, it is like alphabet that we assume is already known.
Great.
But for like very basic level of quantum theory, it is like necessary minimum.
Okay. We have that, and we have the T sub n, right? And so I'm still trying to understand why we're getting rid, how we're getting rid of that, how that T sub n is still problematic. I know there's the square root of the r, or the derivative of the r. You said the big R. The big R is the problem for that one.
Yes, because okay, I've got your question, and let me add something. So phi sub a depends on r lowercase and r uppercase. Chi sub a depends only on r uppercase.
Okay.
Therefore, it will be. Therefore, you do not see it. I'm showing it on the other screen how it goes with focusing. So, when we apply this operator to this product of our capital functions, it will be derivative of a product,
Got it.
which is like derivative of first times second unchanged times derivative first unchanged times derivative of second.
Right.
This is the bad guy in the whole story.
Right.
And there is no reason to keep intrigue. We will assume that it is so small that we will drop it.
Okay.
So unless we are considering explosions or photopolymerization, we can drop this term.
And that's why we keep that one on the right in the red in mind. That helps us come.
Okay, I do not want to decept you in anything. This is not part of equation.
Okay.
The equation,
okay.
the equation is only here,
Okay. Got
and
it.
those are side notes.
Got it. Okay.
Okay?
Right.
Good. Thank you for the questions. It's the first time of this class when it was considered in so much details. Okay. So last slide was important. Here is the same thing. Here is the orthogonality that we are going to practice. So here is the same equation, first, second, third, fourth, and the third one we replaced Hamiltonian by eigenenergies. Right? Ben and Gage can tell us what this drawing means.
Well, wasn't that a rabbit last semester?
Yes. Okay, I can make it a rabbit. But what's the scientific merit of this highly intellectual figure?
The snake eats the rabbit and then they're both gone, if I remember
Perfect.
correctly.
Anyone objects it, or anyone needs more details? So, if mathematically we will have an equation that includes both Kronecker delta and summation sign, they both will disappear. And if I'm a 4-year-old kid studying Born-Oppenheimer separation, I would say that summation is like a snake and Kronecker delta is like a mouse or like a rabbit.
What if the rabbit runs away?
Huh?
What if the rabbit runs away?
It will be different theory. But but here they both disappear. So let's look around what is going on. So I'm not touching the first term, which will be, because it will be tricky. We'll discuss it separately. But next three. These either constants or operators, they do not affect 5 functions. So we can swap order. You put this V, E, W, you can put it up front. It's very rigorous quantum commutations. Nothing prevents us from doing it. We are legitimate to do so. So we are having our orthogonality relations. So phi sub b, and we are intentionally put different index here. So phi star sub b, phi without star sub a, integration. Phi star sub b, phi star sub a, phi star sub b, phi without star sub a, integral. So each time we see this integration, it will be converted into Kronecker delta, right? Which will partially fulfill my life dream. Get rid of phi function. Good? But nothing is for free. Instead of phi, I'm getting delta. With 2 indices instead of 1. And before, in front of this delta, I do have the summation. Summation and delta, summation and delta. Snake and rabbit, snake and rabbit. They will disappear both. Again, nothing is for free. As a price, when they disappear, anytime any object inside the summation had index A, it will flip to index B. You want to believe me or you want me to prove? Here it is. If you have a construction summation over A times delta AB, which means 1 if they coincide, 0 if they don't, times some progression with index A. If indices are, if A is not equal B, this term disappears. If A equals B, this survives. But index instead of A will be equal B.
Oh.
Make sense? So here, I'll probably break it down. Here, instead of this blue circle, it will be just chi sub b. Here will be also chi sub b. Here will be also chi sub b. So we are coming very close to obtaining Schrödinger equation for chi wave function, the nuclear wave function. And we would have it if the first term will be nicer to us. But it is not. So we need like make snapshot of this stuff, and then focus only on the first term.
Now,
the first line. Yes,
will
please.
this lead us to this?
Yes.
So we're leading to that.
Oh yes. Oh
So
yes.
I'm like following you through, trying to, because what's up there is we've got the A and the B. So okay, I get it. I think I see the steps that are happening here. We're going to be mixing some stuff together. Okay, all right.
So right now, yeah, oh yes.
Okay, so it's saying that after we, can I have the pointer?
Oh please, please.
So you're saying that after we multiply this and we do the integral, we get delta
Perfect.
AB.
Yes.
Is this just a delta, or is this like a differential?
No.
Well,
So like if we would try to close our eyes and describe equations, we need to give specific names for each. So this will be called Kronecker delta.
Okay.
Kronecker delta is equivalent to a matrix which has ones on the main diagonal and zeros everywhere.
Okay. All right.
Make sense?
Yeah. So that's what we have here.
Yes.
All right, and every time we, and you stated earlier that every time we multiply this with the summation, they kind of cancel out.
Yes.
Okay.
So I'm going to focus on the first term. Integral phi star b summation a t sub n chi sub n phi a, and somewhere either at the beginning or at the end we should put dr. Okay? So right now I'm going to focus only on these three terms, three factors. So t sub n is minus h bar square to m capital to dr squared, right? Second derivative, because p squared, p is one derivative and p squared is second derivative. Then chi sub n just depends on r, and phi sub a depends on both r lowercase and r uppercase. So we need to practice the second derivative of this product. So d2 dr squared of chi should be a not n, chi sub a of r times phi sub a rr. So we can take one derivative and then another derivative. This chi times phi. So if we take the first derivative, so we are getting d chi over dr times phi function unchanged plus chi function times d phi dr. Okay? This doesn't bother you.
Wait a minute, hold it. What is the, I'm sorry, I'm having trouble reading it. It's the partial derivative, that first term in the bracket, on the bottom. Partial derivative.
Are you okay up to here?
Yeah, perfect.
Okay,
It's-
now I'm keeping these outside derivative in not changed.
Oh,
and just practicing things inside the
gotcha. So still, that's still at
So we
chi.
apply derivative to chi
Yeah, that's chi.
and do not change phi.
Got it.
Then we keep chi and apply derivative to phi. So we got two terms. Now we are going to apply derivative to each of these two terms. What will be the total number of terms after this? And two of them will be similar. But generally it will be 4. So from the first pair, you get d2 chi over dr squared times phi plus d chi over dr times d phi over dr. From the second pair, you will get d chi over dr times d phi over dr plus chi d2 phi over dr squared. Any objections? Seems logical. Derivative of a product. Do you see any similar terms that we can merge?
Oh yeah.
It's a wake up test. If you are not
Middle.
sleeping, you're not sleeping. Certified. See, middle two terms are identical. So we can cancel, cross one here and put just factor 2. So let's think and analyze what we have. And later on we can put back like factors of this age, bar, mass, but generally. When we apply second order derivative of position of nuclei to nuclear wave function, we are in chocolate. We are doing the right thing. Very natural, very intuitive, right? So this part will be taken kinetic energy of nuclear motion. Very standard. So this is a good term, not challenging. But these two are really crazy. So the last one, you do not change wave function of nuclei, but you apply, you find contribution to nuclear kinetic energy due to electronic motion or through some electronic wave function. It's really crazy. And this is a product of cross term that includes dependence of both nuclear and electronic wave function on position. We do have one person in class who, at least one, maybe more, who is practicing this equation or is expected to practice this equation every day. So, first derivative of nuclear wave function over nuclear position is momentum, right? And derivative of electronic wave function over nuclear position is response of electronic state to change in the positions of nucleus. Gradient of electronic wave function in respect to change of positions. So it is what we will cover as a top most complicated thing at the very last lecture as non-adiabatic coupling. So right now we are reaching the top in mathematical complications. We'll go downhill for simple things and we will recall it back later. Yes?
Could you say that one more time about the first and second derivative? I just want
Absolutely. I can repeat it every day. No, I'll keep standing. I was thinking about to sit down. So, we do have three terms, right? The chi function is wave function of nucleus. Phi function is wave function of electrons. Second derivative of nuclear position is kinetic energy. So if we apply nuclear kinetic energy operator to nuclear wave function, it is good. First term is really good. Not challenging, intuitively clear. But when we're looking on the second and third term, they are mind-throwing. We just glance for them, neglect them for the whole semester except the last lecture, and live a happy life.
So the second derivative is the kinetic energies.
Well, it's very counterintuitive thing. If you find contribution to kinetic energy of nucleus, of ions, due to peculiarities of electronic wave function. Like how shape of electronic wave function may affect velocity and kinetic energy of nucleus. I would never assume it without deriving equations. It's mathematical consequence, not intuitive thinking. And the middle term is a little bit more intuitive, but still crazy. So it means that there is a contribution to nuclear kinetic energy because of the momentum of a nuclei times gradient of electronic wave function over the position of ions. So it's how electronic wave function changes if we shift ions.
So this one's shifting the ions, and then the first one's shifting the electrons.
In this
The The harder part. The harder part.
Wait. Oh. In the last line,
Mm-hmm.
we are not shifting electrons.
Oh.
We do not. We take derivative only over R capital, which is positions of ions. So we are not shifting electrons.
Okay.
But we are applying this derivative either to electronic or nuclear wave function.
Okay.
And therefore we get some crazy terms. Good?
Yes.
Whew. 7:13. We'll finish soon. Don't worry, we are over the hard part. So this is the same thing as we had before. Last three terms are just contains chi of B. Upper term contains chi of A times this phi B, phi A, and the nuclear kinetic energy operator inside. And this matrix element, generally, especially when something explodes, is not zero. Okay? It is actually what we already did. So, we are going to, that's it? Huh, I thought I'm going to tell more. Okay, it's time to wrap up. You remember, it is these same equations that we derived and discussed. Okay. So, the idea of these two gentlemen with photographs that I distributed last time, Born and Oppenheimer, is that we keep the good term and assume that bad terms are negligible. Any single piece of computational chemistry software that you're practicing assumes that these two terms are zero, which is okay if it is low temperature, absolute zero, no chemical reactions. But if it is elevated temperature, if it is a heavy laser field, if it is some photo-excited charge transfer and combined with nuclear motion, if it is explosions, Born-Oppenheimer approximation will not work. This is not a part of any freely downloadable or freely buyable software. But we need, typically, for most of the practical parts, we will just neglect these terms. And we will call it Born-Oppenheimer approximation. So that's maybe the only thing that you need to memorize. For traditional computational chemistry, electronic structures theory, we are working in Born-Oppenheimer approximation, neglecting quantum exotic contributions to nuclear kinetic energy. And if we drop these terms, then our molecular Schrödinger equation will convert into Schrödinger equation for nuclear wave function. So the term, when we do not have strange parts, when we have only like standard, one can call it pure nuclear kinetic energy, plus nuclear repulsion, plus electronic part, times unknown nuclear wave function equal energy of nuclear wave function state times nuclear wave function. So Schrödinger equation for nuclear wave function, while neglecting non-adiabatic terms. Enough for today. So, meeting is done. Let me show the most interesting slide. Have a nice weekend. I'll stay here just in case any of you have questions. So I'm looking forward to get the democratic practice of paper.
Oh my god. Thanks. Oh, nobody wants to do JMO?
Can I have it?
Anyone chosen open Bible? Do you practice it?
Yeah, it is.
Excellent.
I did Avogadro.
That's good. So everyone is welcome to the part Please,
I have questions. so-
please, I'll stay here to answer.
No, I think I almost have this. I just want to make sure. Can we go back to that term that you were showing in the last part of the calculation? Or, no, not that. No, before that, the most important slide.
No, probably.
No, I think we went to.
No, before. Yes.
Okay.
Only my third is.
Okay, no, not. It's where we did the kinetic of the nuclear motion. I'm not doing a very good job of explaining this, but it's the delta
And I already had some already.
second derivative of the r, the big R. Yes, there. Sorry, colors threw me off. Okay. So I understand that the blue,
When is
the blue part, not that. Yes, that one. Is we're applying it to the ions, and I'm trying to understand. If you could say that like one more time, we're applying it to the ions, and it for the electronic and the nuclear part. Is that right?
Yeah.
So, at the beginning, we are applying. We are applying.
You should make a joke.
Second derivative or positions of ions.
Positions of ions. Okay. Which I
To
got.
product of nuclear and electronic wave function.
Okay. That was it. To the product. Okay. Hold on. Now I understand. So
I'll do that.
I go
I
maybe
have to go home. I have to eat. I have to do stuff tonight.
that's all I want to know. That was
Okay.
it. That was it.
Excellent. Thanks for patience and for surviving this really hard and
Actually,
complicated.
I think this was better than the Tuesday one.
I'm more excited about this one because it is practically important.
Yeah. That one confused me. Because this one shows equations. I like equations.
Any more questions?
Are you gonna upload this?
Yes, we will see right now.